Hey class, we are going to look at parallel circuits on this presentation. Okay. Okay, so the definition of a parallel circuit is a complete path of electricity to flow in more than one direction. So let me repeat that. A complete circuit that has more than one path for the current to flow. Okay. When we talked about series circuits, we said that series circuits only has one path for electricity to flow. Parallel circuits have more than one, okay, two or more. The other important thing to note here is the current flow through each leg varies depending on the resistance in that branch. On a parallel circuit, each branch is called a leg or a pathway, so to say. Now, the resistor in that specific leg will determine the amperage. Okay, so remember the amperage does the exact opposite of the resistance. Okay, so resistance goes up, amperage goes down, amperage goes up, resistance goes down. Okay, so we're going to show a couple pictures. I think the pictures are going to be easier to understand. As always, if you see anything that's highlighted, make sure you write it down. It's going to help you for sure, especially when it comes to the test. Okay, so we're looking at a parallel circuit. If you'll notice on a parallel circuit, we have three ways of power and we have three ways or three paths of ground as well. There are three bulbs here. All these bulbs are wired in parallel. So let's just say that these bulbs here are tail light or brake light bulbs. Sorry. So we have our left brake light bulb, we have our right brake light bulb, and we have our center brake light bulb. Okay. If you were to say, let's just say that this bulb here on the left side went out. Okay. So the bulb burned out, right? If the bulb burns out on the left side, does that mean that the other two are going to burn out? If you notice, if anyone's ever had a brake light bulb burn out or even a headlight bulb, you'll notice that the other bulbs don't burn out. There's nothing that happens to those other bulbs. That's normal. That's how cars are designed. Okay, so that means that each bulb or each circuit, each electrical load gets its own power and gets its own ground. So now if we look down here, we'll notice, again, the grounds can bolt directly into the body. And we'll notice here that there's a ground for the left bulb, there's a ground for the center bulb, and there's a ground for the right bulb. Each one of them have their own grounds. Okay. The other thing we need to notice too is that there's a power wire for the left bulb, there's a power wire for the center bulb, and there's a power wire for the right bulb. Now, this is how parallel circuits are designed. The one thing that they are shared, at least in this drawing here, is the fuse. Okay, so the fuse is the only thing that's shared in this picture. Is this true of all vehicles? Not necessarily. Depends on the design, depends on the manufacturer. But in this case, if the fuse was to go out in this circuit that we're looking at, would that affect everything? If the fuse blew, then yes, all of them would go out. Okay, all three bulbs would go out. In this instance, in this circuit, this is the only one that is designed like this that we're looking at. But again, manufacturers will do different things depending on the year, make, and model. Okay. Okay, so now we have three laws for parallel circuits. Just like we had three laws for series circuits, we now have three laws for parallel circuits, and they are different. So it is very, very crucial if you want to understand parallel circuits that you write these down and that you memorize them. So I hope you've memorized the series circuit laws. Now it's time to memorize the parallel circuit laws. The first one, the total resistance is always less than that of the smallest resistance leg. So if we go back to series circuits, in order for us to get total resistance, we have to add up the resistors. In this instance, though, in a parallel circuit, we do not add up the resistors. Again, I want to repeat, we do not add up the resistors. What we do is whatever our total resistance number, whenever we find that number, so let's just say that we have a parallel circuit. I'm going to draw a very, very simple little box here, and I have 1, 2, 3 legs coming from this box, which is our 12-volt battery. Okay. Now, this resistor here, and this resistor here, and this resistor here. So we have three resistors. Okay. Now, the RT is, we'll say, equals 4. Okay. Now, in this instance here, I haven't given you the value of each resistor just yet, but let's look at the law. The total resistance is always less than that of the smallest resistance leg. So our RT, in this instance, what I gave you is 4. So that means that the value of these three resistors cannot be less than 4. Okay, that means that this 4, our RT, has to be less than whatever these are. So they can be 4.1, 4.2, 5, 6, 10, 20, 100, and so on. Okay, can they be 3, 2, or 1? No, they cannot. Okay, again, the total resistance, which is this number here in our instance that we're looking at, is 4, is always less than that of the smallest resistance leg. So again, one of these resistors has to be all of them have to be more than 4, but the lowest one could be 4.1, so to say. And that's it. It could not be 4 and it could not be 3.9, according to our first law. Okay. So let's go to our second law. So the second law states that the voltage is the same for each leg. Again, if we go back to the picture before, and we have a 12-volt battery. So let's just say this battery is 12 volts. Because we have voltage coming from the battery and it's going to the first bulb, to the second bulb, and to the third bulb, all bulbs are getting 12 volts. If you were to take a meter and measure your voltage at your left brake light, your center brake light, and your right brake light, you would measure 12 volts at each brake light. Okay, all components in the car get 12 volts. The certain modules will step down the voltage to 5 volts, but it will get 12 volts if it's needed. All right. So again, everything gets 12 volts because everything's wired in parallel. Now let's go to the third law. The third law has to do with amperage. The sum of the individual currents, amperage, in each leg will equal the total current. So in a parallel circuit, instead of adding resistance like we did in a series circuit, in a parallel circuit, we are going to add amperage. Each leg has its own amperage because each leg gets 12 volts. So if I have another, I'm going to draw just 2 this time. Okay, just a little 12-volt battery. I'm just drawing, real quick here. 1, 2. Okay, and we have a resistor here and we have a resistor here. Now let's just say that this resistor is 2 ohms and this resistor is 4 ohms. The amperage on this first leg, on the leg 1, is 12 divided by 4, which would give us 3 amps. The second leg, 12 divided by 2, is 6 amps. Therefore, according to our law, the sum of the individual currents in each leg will equal the total current. So in order for us to get IT, we're going to add a little t at the bottom. It's going to be a subscript t, equals 3 plus 6 in this case, which will give us 9 amps. Okay. So that's what that's telling us. So we're going to add the amperage legs. We're no longer adding resistance like we did in a series. So we have to treat these as 2 completely different styles of circuits because they are different styles of circuits. Okay. We're going to move on now. So make sure, again, go over these laws, memorize them, try to understand them as best as you can. Now we're moving into another type of circuit, another example of a circuit, I should say. This circuit here has 2 resistors. We have 2 bulbs. One bulb is 3 ohms. The other bulb is 6 ohms. There's also 6 total amps in the circuit and 12 volts in the battery. All right. So now as we're coming out of the battery on the positive side, so it's going this way, we have 6 amps. If we want to find total resistance, we could do that very easily because it's 12 volts divided by 6 amps, which will give us 2 ohms for RT. Okay, resistance total. Now to verify, if we check with law number 1 tells us that total resistance is lower than the lowest leg. So 2 is lower than the lowest leg, which is, in this case, 3, because we have 6 and 3. 2 is less than 3. That means the law works out. So we're okay. Now, the amperage, though, the thing that we want to look at in this instance, in this picture, is what happens to the amperage. When two parallel circuits come together, it's called a junction. And that's what this little dot here is. Okay, junction A. Now, as the electricity hits the junction, what happens is the amperage splits. Okay, it doesn't split evenly because it's going to be based on what the value of the resistor is. Now, if we take 3 ohms in this first leg and we multiply it by 4 amps, we will get 12 volts. Okay, let's do the same for the other one. Now, if we have 6 ohms and we multiply that by 2 amps, we will get 12 volts. Okay, so the math works out either way. Any way we want to look at it. The one thing I do want to point out that's not labeled here, so there's a junction on the power side where the 2 legs split. There's also a junction on the negative side where the 2 legs come back together. Now, after this junction, from this point all the way to the negative cable, the amperage in this portion of it, because we have to go back to the very, very first law, or one of the first laws of series, which is amperage is the same throughout the circuit. This leg, this portion, I should say, of the circuit here from the ground, from the junction to the ground, is 6 amps as well. Okay. So we have 6 amps coming out of the battery, splits based on the value of the resistors. And then when it comes back to the battery with the closing junction, it goes back to 6 amps. Okay. Okay, next portion. Now, this is another drawing of a parallel circuit. And again, we want to look at how the amperage flows and based on the resistance values, what we're getting. Okay, so amperage, again, we have 12 amps, we have 12 volts, we have 6 amps coming out of the battery. When it hits the first junction, okay, I'm going to draw the junction right here. And then here's the closing junction. When it hits the first junction, it's going to split. And the value of the amperage is going to be based on the value of the resistor. Okay. If we had a different type of resistor, then the amperage would adjust. If we had a different amount of resistance on leg 2, then the amperage would adjust accordingly. Okay. This is the same image as the previous slide, but it's just drawn in a different way. Instead of using pictures of bulbs, it's using resistors. Okay. But again, they are the same thing. They look, they're drawn exactly the same. Okay, let's go to another one. So now this one does not give us voltage and it does not give us amperage. Instead, what we're just trying to find is total resistance. In order for us to find total resistance, there is a mathematical formula. I will give this to you right now. Let's draw the mathematical formula. This is a long formula. It is written in the textbook and is written in the lecture. Okay, so let's do 1 over RT. This is the formula to find 3 resistors equals 1 over R1 plus 1 over R2 plus 1 over R3. And then so on and so on and so on and so on. So what that means is, in order for us to find RT, we plug these numbers in. We plug 3, we plug 4, and we plug 6 in this instance. We plug them into our equation down here. Then in order for us to add fractions, I don't know if you guys remember, if anyone remembers how to add fractions from, basic math, and it may have been a long time since you've done that, but in order to add fractions, we have to get the same number on the bottom, which is called the denominator. Then we can add the numerators, which is the number on the top. Okay, so there's a little bit of math involved in this equation. Again, this is for 3 or more resistors. Okay, 3 or more resistors. There's a different formula for 2, which I will show you in just a minute here. Okay, so now we have 2. So here's 2 resistors. We could find total amperage because the voltage is given, okay? But I want to show you the formula. So this is the formula for two or more resistors, or sorry, for just two resistors. So two resistors. So make sure you write down this formula too as well. So RT equals R1 times R2. All that is over R1 plus R2. So that's our equation there. And again, this is for two resistors only. If you have three or more resistors, you'll use the other equation. So we can just plug the numbers in here. This is relatively easy. I know we do have the 12 volts over here, and we could theoretically just find amperage on each leg, and we will do that afterwards. But let me show you how to do this problem, how to solve this problem. We always want to find the usual thing. So we want to find E, we want to find RT in this case, and we want to find IT. Okay. So in order for us to find, sorry, let's go back a little bit. The voltage is already given. It's 12 volts. Okay. To find the RT now, we just plug in our numbers. So let me fix that. That doesn't look very good. RT equals R1 is 3 times R2 is 4 over R1, which is 3, plus R2, which is 4. Okay. Now, all we do is just multiply across and add on the bottom, and that's it. And then we can reduce. So 3 times 4 is 12. 3 plus 4 is 7. Now, RT equals 12 over 7, but we don't want to leave this as a fraction. So we need to take out our calculator real quick, and let's find the reduced number in a decimal form. 12 divided by 7 will give us 1.7, and it's a longer number than that, but I'm just going to do 1.7 to make it real easy for now. So now our RT is 1.7 ohms. Okay. Can we figure out total amperage from here? Oh, easily. We can do 12 divided by 1.7, which would give us 7 amps. There's a longer decimal to it, but we're trying to keep things simple for right now. In order for us, we can verify this too. Okay, so 12 divided by 4, because we have 12 volts, and we have, 12 divided by 3, we have 12 volts, and we have 3 ohms of resistance for leg 1, or R1, which will give us 4 amps. Okay, then 12 divided by 4 ohms for resistor number 2 and leg number 2 will give us 3 amps. The third law in parallel circuits tells us that we need to add the amperage legs together. 4 plus 3 is 7. Okay, so the math works out either way. We could have found the amperage in each leg first and find IT first, and then just divide 12 by 7. Or we could find the RT first and then divide the resistance total by the voltage. So either way you can do it. You can do it two different ways in these problems. There is one instance where you do have to use the longer equation, the resistance equation, and that is when voltage is not given. Okay, you have to. There's no way around it. But if voltage is given and then we're trying to find resistance or amperage, you can use this amperage per leg way to find it and then add the amperage legs. Okay, you'll see there's different ways to do these equations to try and figure out what's going on here with amperage and amperage, resistance, and voltage and how they all interact with each other in a parallel circuit. Okay, so let's go on to the next slide here. Okay, now this is something that needs to be understood as well. Anything, again, that is highlighted, make sure you write it down and understand what's going on. As additional branches are added to a parallel circuit, total circuit amperage increases. Okay, so what this is saying is that we have 3 legs here in this circuit that we're looking at. We have 12 volts, we have first leg is 3 ohms, second leg is 4 ohms, and third leg is 6 ohms. Now, if we were to add another leg, it could be another leg of 3, 4, 6, or just something else. What would happen is the total amperage in the circuit would go up. Now, the reason that's important is because if we have one fuse that is protecting all three of these circuits, these legs, that means that if we add another leg, the amperage is going to go up. So we have to be very conscious of how far the amperage goes up, because the amperage goes up too much, we're going to have to change the fuse. The fuses have to be upgraded or increased in amperage. And also we need to make sure that the wiring is able to handle that type of amperage too as well. Okay, so that's why it's very important. The second bullet point here says, as additional branches are added to a parallel circuit, total circuit resistance decreases. So it goes down. Now that does make sense, because if we think about it, let's go back to how amperage and resistance work together. If we're increasing amperage by adding more legs, amperage goes up. What has to go down? The resistance has to go down, because amperage and resistance work the opposite of each other. Okay, so amperage is going up, resistance is going down. If we increase resistance, we decrease amperage. Okay, so they're always doing the opposite of each other. Now this slide here, if you want to take, pause and take some notes and look at this a little more closely, what this shows you is how to do some of the equations with a calculator, with a scientific calculator. Okay. I'm not going to go through this here. If you want to, if you have a scientific calculator and would like to go through that, you are more than welcome to. You can use calculators in this class. I don't prohibit students from using calculators at all. Okay, I encourage it actually. And same thing here. Again, if you would like, you can pause the video and look at this example here and figure out, how they're using the calculator to find the answers. Okay, one last thing before we get into some equations here. There is one trick to find the total resistance when we have all resistors that are the same. Okay, this only works if all resistors are the same in the parallel circuit. In this instance, this picture that we're looking at here, we have 12 ohms for all 4 legs. So 12, 12, 12, and 12. Now, if we had all of them were, say, 3, or all of them were 5, or all of them were 100, we can do this trick. If we have 3 of them that are the same, such as leg 1 is 12, leg 2 is 12, leg 3 is 12, but leg 4 is 10, but then we could not do this trick. Okay, so the trick is very simple. We take the value, well, in this case, it's 12 ohms, okay, and we divide by the number of legs there are. So there's 4 of them, and then that'll give us 3, and that equals RT. Okay, so if we were to work out the math, we could do all the math and figure, and verify ourselves, but the answer we would come up with is 3. So 3 ohms of total resistance in the circuit, and 3 is less than the lowest because the lowest is 12, and 3 is lower than 12, so that fits the law for parallel circuit law number 1. Okay, so everything works out. If we wanted to find the amperage real quick, we could do that, because it's 12 volts and 12 ohms for each one of them. So 12 divided by 12 is 1. So we have 1 amp, 1 amp, 1 amp, and 1 amp, and that goes for all legs. Then we can add these together, which would give us 4 amps for total resistance, or total amperage, sorry. And then we could divide 12 by 4, which would give us 3, which is up here, which verifies everything. Okay. So again, these are not difficult as long as we understand how they work and we understand the formulas and how the formulas work as well. Okay. So again, these are not meant to trick you. The math is relatively easy. And the reason we're going through some of the math is for the theoretical knowledge. So we understand what's going on here with the electricity as it works. This is all theory based. This is how engineers design cars and work, fix, sorry, not repair cars, but use the theoretical knowledge of electricity to design vehicles. Okay. Let's look at this one again. So this one is just like the last one, except instead of having 4 resistors that are same, it only has 2 resistors that are the same. So we have R1, which is 12, and R2, which is 12. So we can do the same exact trick. We can do 12 divided by 2, which will give us 6. And that is our RT. Okay. E, in this instance, is given, which is 12, and I is also given, which is 2, and the math works out. So our RT is 6. Okay, so all the math works out here, no problem. As we move on to the next problem. So this problem here, we are looking for R3, which means that our voltage is given, our amperage is given, and resistor 1 is given, and also resistor 2 is given, but resistor 3 is not given. That's what we need to find. So how can we find this? Okay, we can work backwards in a sense with amperage, or we can try and we could use the formula for three resistors. We could do that. There is going to be some algebra involved with that, though, some basic algebra. If you're comfortable with that and you can see that, then you are more than welcome to find the answer that way. However, I'm going to do it a little bit easier this way. So what we're going to do is we're going to use basic Ohm's law, which is E over IR to start with. Okay, so we know E, which is 12. We know I, which is 12 also. If we do 12 divided by 12, that'll give us RT, which is 1. So RT equals 1. Okay. We're not there yet. Okay, we could use that answer and plug it into our longer equation, which is 1 over RT plus 1 over R1 plus 1 over R2 plus 1 over R3. Since we have RT, we can plug that in along with the 4 and the 2, and then leave R3 as X, as our variable that we're trying to find. Again, that will involve algebra. I want to kind of stay away from algebra for right now. So what we could do is find amperage per leg, because we know that the formula for amperage, we just need to add them up. So IT will equal 4 plus 2. I'm sorry. I don't want to go ahead of myself here. Let's go back here. I want to find amperage first per leg. 12 volts divided by 4 ohms will give us 6. Sorry. I'm messing up here a lot. I don't know why. Okay. 12 volts divided by 4 ohms will give us 3. There we go. 3 amps. I was moving ahead. Now 12 volts divided by 2 ohms for leg number 2, that will give us 6 amps. I was looking ahead instead of looking at what I'm supposed to be looking at. So now what that tells us is that IT equals 3 amps for leg 1 plus 6 amps for leg 2 plus the amperage for leg 3, but we don't know that just yet. But can we find it? We can definitely find it, because we actually have the answer for IT already. And it is 12 because it was given to us. So we're going to take 12 equals 3 plus 6 plus what will give us 12. The 3 plus 6 is 9. So we have to take away 9 from 12, and that'll give us the answer. Okay. So the answer for X is, in fact, 3 amps. Okay. So what we can do is we can plug in 3 up here. So 3 amps. Okay. But we still haven't found the the resistor, which we're actually looking for. Okay. But now we can find it relatively easily. We take 12 volts and we divide it by 3 amps, because that's what we have over here for leg 3. And that will give us exactly 4 ohms. Okay. It's just like leg 1. Okay. So 3 amps and 4 ohms, multiply them together, and we would get 12. So the math works out on all of them. Okay. And our total resistance, which is 1, is lower than the lowest leg. So the lowest leg here is 2 ohms of resistance for leg 2, and 1 is lower than 2. So we're good. The math works out. Okay. So hopefully everyone was able to follow along with that circuit there. We're going to move on to a couple more, and hopefully you can try these on your own. So this is a relatively easy one, because we kind of just figured this one out a little while ago. So we have 4 resistors, and all the resistors are the same: 12, 12, and 12, and 12. 4 12s. So what we could do is we can do the trick, right? We can do 12 divided by 4, which will give us 3, which are RT, which is our RT, sorry, equals 3 ohms. Our amps is given, which is 4. So IT equals 4 amps. Can we figure out the E pretty easily? Yeah. 3 times 4 will give us 12 volts. Okay. And that's what we're looking for in this circuit here, was our voltage. All right. That was a very simple one, I think. Let's go to the next one. So this one, we need to find amperage. Okay. So we can't do the amp. Well, we could do amperage per leg, which is the way I'm going to do it, the way I'm going to show you. If you wanted to do the 1 over RT to find 1 over RT plus 1 over R1 plus 1 over R2 plus 1 over R3 to find the total resistance, you can. And what we could do here is, let me show you how to do that real quick. 1 over 8 plus 1 over 8 plus 1 over 4. And that'll give us 1 over RT. Now, again, we got to find the common denominator for all of these. So the common denominator is 8 for all of them, because 4 will go into 8, 8 will go into 8. So 8, the two 8s we leave the same. So R1 and R2 we leave the same. In order for us to change 4 to an 8, we got to multiply it by 2. If we do that to the bottom, we got to do that to the top. And that'll give us 2 over 8. Now all we do is add, so I can cross this one out. All we do is add the numerators now, since all the denominators are the same. So our answer would be 4 over 8, because we're adding 1 plus 1 plus 2 will give us 4 over 8. Okay, now here, I'm going to rewrite it up here, because what I'm going to do is I'm going to write 1 over RT equals 4 over 8. That is not our answer yet. There's one big issue that we need to take care of. We cannot leave an answer as a fraction, but also the RT is under a 1. It is the denominator. The RT cannot be under 1 for this answer to work. What we have to do is we have to either cross multiply, or the easy way is to flip it. Okay, this is called the reciprocal rule. So the reciprocal rule tells us that we can flip this, meaning we can put the RT on top. If we put the RT on top and it goes over 1, any number, any letter, any variable over 1 is just that number, that variable. Okay, so we actually don't need to write the 1 over 1 anymore. We can just write the RT by itself. But if we do that to this left side of the equation, we got to do it to the right side of the equation, the right side of the equal sign. And that has to be 8 over 4 then. Now we can reduce from here. 4 goes into 8 2 times. So our RT is 2 amps. Okay. We have 12 volts. It's given, and we have 2 ohms of resistance. 12 divided by 2 would give us 6 amps. Okay. If we wanted to find it per leg, what we could do is 12 divided by 8, which is 1.5. This is amps for leg 1, and it'll be the same for leg 2 because it's the same variable, same number. And then 12 divided by 4, which is 3. Then we can add these numbers up and we would get 6. Again, so there's 2 different ways to do this. I mean, I prefer the amperage per leg way, but I did want to at least show you the mathematical way here. Okay. Let's move on to the last equation. Okay, this one, relatively easy. Actually, everything's already given, so we actually don't have to find any answers, but I do want to show you at least how to do the formula for two resistors, okay? We have, oh, actually, sorry, this is a series parallel circuit. This one, I don't want to show you the formula. I think I've already shown you the formula how to do, how to find two. And it is in our lecture notes, so make sure you go through the reading, go through the textbook as much as you can, and you know, do as many of the problems as you possibly can. With parallel circuits and series circuits, practice does help a lot. You have to do them multiple times over and over and over again. Now, this first one here, what I want to show you here is that we have a series and then we have a parallel. So this is just a precursor to the next lecture. So in the next module, we're going to go over series parallel circuits, which is when we combine both of those types of circuits together. So we will combine series and parallel together. Now, as we're going through, we have a series portion. So this portion here of the circuit, the first resistor is in series because as we can tell, there's no breakage between. The breakage happens right here, happens here at this first junction. Then we have electricity that goes to these two separate resistors. Okay, then it comes back into this junction here. Then it goes back to ground. All right. So this is a series parallel circuit. They are dealt with differently because we have to combine all laws from both series and parallel. And we will get to that in the next one. Okay. I don't want to go over on the math on this just yet because it will be in the next module. Okay. So hopefully you enjoyed this section and hopefully you learned something. Again, always reach out to me if you have any questions. I know these types of circuits can be difficult. If you have any questions about these, please reach out to me and we can go over these more. Okay. Thank you very much. Have a good one.